Hello, y'all. So we left off on this problem here with the cube with 6 conducting plates, size A and A. And we'll go ahead and work from here. So, and actually it looks like they placed it half and half. So it's negative A over 2 and A over 2 for the X and so forth. So origin is in the center. The plates at V plus and minus A over 2 are held at potentials plus and minus V naught respectively. So this has V naught, and if I was to make a bottom plate here, this would be negative V naught. And all of the different sides are grounded. I forget the grounded symbol. Is it this? Maybe it's that. See if I have it noted. I don't think I do. The separable solutions, it gives us the form, these two forms, and N and M are non-negative. So solve the boundary value problem for V inside the cube. All right. I may look to the solution for this one. So boundary conditions, that'll be what they gave us. So V x, y, z over 2 equals V naught, and V x, y, negative z over 2 equals negative V naught. So what they're saying is we have to either multiply sine times that or cosine times that. Um, the halfway point equals a value. So here is we have to draw a rough estimate. We have at 0, and this is the z-axis. At 0, we have something, actually we have nothing, and at positive, it's a high value. At negative, it's a negative value. So this is consistent with sine. So that means that our equation would have this form. As far as the separable solutions, V, X, Y, Z equals hyperbolic sine AN M V cosine 2n plus 1 pi x over A, and cosine 2m plus 1 pi y over a, because for the other axes, it has to be 0 at the boundary. Excuse me, I guess it say 0 away from the boundary. So away from the boundary, we have 0. At least away from the center, we have 0. So sine is 0 in the center, but has a value later. Cosine has a value 0 away from the center. So therefore, it's cosine for the others. That makes sense. So this is the form of the potential. The hyperbolic sine KNMZ cosine 2n plus 1 pi x over a, and cosine 2m plus 1 pi y over a. So another boundary condition, Laplace's equation must be satisfied. So Laplace's equation must be satisfied for this to be a real potential, like a real potential in nature. So we can actually check that. Try that. Let's see if we can solve for Km, because we don't know what that is. So we know that this equals dot product V. So this equals del dot X V Y V Z V. So that equals this dot. So if I take a derivative with respect to X, hyperbolic sine stays the same. And we have negative sine 2n plus 1 pi x over a cosine 2m plus 1 pi y over a, and then times 2n plus 1 pi over a. And to take the, and I forgot to put my so the easiest way to implement this. Well, that is dope. That is one comma. Hold up. To take the partial derivative with respect to y. So this will also be negative hyperbolic sine a n m z sine 2n plus 1 pi x over a. And then we have cosine 2m plus 1 pi y over a. And then we're going to have to multiply by 2m plus 1 pi y over a. And then the derivative with respect to z, I believe that should still be k n m hyperbolic cosine k n m z cosine 2n plus 1 pi x over a cosine 2m plus 1 pi y over a. Has to all have a dot product with del again. So the first one will be just the partial derivative of x. And like I wrote the cosine in the wrong spot here. See how this looks? The partial derivative of x with the first one, it'll be negative hyperbolic sine k n m z cosine 2n plus 1 pi x over a cosine 2m plus 1 pi y over a, and this will be 2n plus 1 squared pi squared over a squared plus, or I should say minus, hyperbolic sine k n m z cosine 2 2n plus 1 pi x over a cosine 2m plus 1 pi x pi y over a, and then 2m plus 1 squared pi squared over a squared. Uh, and then we have also with respect to z, negative sine to put negative a squared and m sine hyperbolic sine k n m v cosine 2n plus 1 pi x over a cosine 2m plus 1 pi y over a, and this is supposed to equal 0. Question is, how did they solve this for 0 and even show the steps. So it seems like it must be some kind of rudimentary thing. Seems like, okay, so each of these things are multiplied with a sign. So if K N M Z equals N pi, so K N M equals N pi over Z. That's not what the book has. It does seem like if K and M equals N power over Z, the sign term will be 0 for all of them. And then all the sounds will be 0. Would be my mistaking the details of hyperbolic sign. Look it up real fast. So hyperbolic sign x equals e to the x minus e to the negative x over 2. And cosine of x equals e to the x plus e to the negative x over 2. Currently, hanging cables make a hyperbolic curve. Like a hanging cable makes a hyperbolic cosine curve. That's interesting. Must be an easier way to do this, but this is not the value they got, but I'll go with it for now. And I'll just put a question mark on this. Look at later. So we know from earlier that V is this. N and M. So we can add a summation to account for each of the N's and M's. So we know that v x y a over 2 equals v naught. So that's going to equal looks like I'm missing one thing here, which is the coefficient Mn, because it be 1, but that allows for any coefficient we might need. So V naught would be the sum, draw the components of that, Cmn, and let it be hyperbolic sine A and M A over 2, then cosine 2n plus 1, and pi over 2, cosine 2m plus 1, pi over 2. Still an x and a y there. So I have to remember that that's only for z, not for x and y. So we could use the Fourier trick, which is a way to uh, extract certain components by multiplying by a certain integral. So I'm going to multiply both sides by the integral negative a over 2, a over 2, integral negative a over 2, a over 2, cosine n prime 2 pi x over a, cosine m prime 2 pi y over a dx dy. Now, n pi x and m pi x. So that means I have this integral, negative a over 2, v naught, cosine n prime 2 pi x over a, cosine m prime 2 pi y over a, dx dy equals double integral negative a over 2, sum m n to the infinity of Cmn hyperbolic sine Kmn a over 2 cosine 2n plus 1 pi x over a, cosine 2m plus 1 pi y over a dx dy. So only when n and m are equal do we have a non-zero value. So if finality cosine 1 over L integral negative L to L cosine n pi c over L cosine m pi t over L dt equals 1 if n equals m and they equal not 0, 0, m doesn't equal n, and 2 if n equals m. Uh, suppose this is a constant. Remember what this is. What we did here was this will be 2n pi x plus pi x over a. So we can say this is 2n plus 1 pi x over a. So we can say this is n plus 1 half 2 pi x over a. And we're going to call this m prime or m. M prime equals n plus 1 half. M prime equals m plus 1 half. And I left off some of my integral here. I also have to multiply. Let me actually put it on a different line. Cosine n prime 2 pi x over a cosine m prime 2 pi x over a dx dy. Now we have double Fourier tricks. With these two will be related to each other. And here it looks like I need the other value thing, but perhaps not. What's going to happen is if these are equal, I think I could just take the integral of the left side. That'll be V naught sine n prime 2 pi x over a sine m prime 2 pi y over a. And this is going to be times a squared divided by n prime 4 pi squared. Just the integral of the left side, and it's going to extract only the ones that matter, where m and m are the same. So it'll be Cmn hyperbolic sine Knm a over 2. That takes care of the integral. And actually simplify this a bit. This is going to be V naught, we know sine we're only going to get a value when m and n are equal. There's a way to simplify this, but I don't remember it. We can say Cmn equals V naught sine n prime 2 pi x over a sine m prime 2 pi x y over a squared over n prime m prime 4 pi squared sine hyperbolic sine k n m a over 2. Of this. So we say I have Cm. We have Km from earlier. So this is the potential we were looking for here. We solved for Cm here. And we solved for Km here. So we have everything we need. So now we know what the potential is. We sort of positive part should be the same if we put in negative because they're just opposite signs from each other. So there we go. So that's that problem. So these are getting more complicated as we go. I'll take a break and be back later.